Okay, so there could actually be many more types of sequences other than arithmetic and geometric. Hopefully you have a feel for those now. And hopefully you also have a feel for recursive and explicit definitions. And I'll give some more of those. Okay, all right, so let's look at another type of sequence. Let's look at this sequence. Okay, let's say it's like 1/2, then 2/3, 3/4, 4/5, etc. Is this arithmetic, geometric, or neither? Okay, so what you'd have to test is you'd have to test 2/3 minus 1/2, okay? Is that difference the same as 3/4 minus 2/3? And of course you could test it with many of those things. But hopefully you'll see, even maybe without doing those calculations, that the difference between successive terms is actually getting smaller. Like, of course, like, you know, at the end, not the end, but, you know, you're going to have 99 over 100 and then 100 over 101, etc. That difference is getting smaller and smaller. So there's no common difference, right? And if you think about it, there's not going to be a common ratio either. Now, to test that one, it's kind of icky as well. I'd have to do a later term over a previous term. I can't get these right today. 2/3 over 1/2. So I'd have to, like, you know, figure out what that ratio is. So probably, I guess I'd multiply that by 6 over 6 to figure that one out. So 2/3 of 6 is 4, 1/2 of 6 is 3. Okay, so I get 4/3 as that first ratio. Let's just test if, like, the next ratio works out. So it'd be 3/4 divided by 2/3. Okay, so I guess in this case I'll multiply by like 12 over 12. Let's see, so 3/4 of 12 is going to be 9. And then 2/3 of 12 is going to be 8. So I don't, like, these two numbers are not the same common ratio. Like, once I put, like, a previous term over an earlier term, and obviously you could continue to find that the ratios are going to differ or whatever. So it neither has a common difference, right? Take a term and subtract the previous term. It neither has a common ratio if I put a term over a previous term and look at those things. So this would be a neither sequence. The question is, could you come up with a definition for it? And you can. So you could say a sub n is going to be equal to, okay, it's going to be equal to n over n plus 1. Let's see how that works. Okay, so a sub 1 would be, n is 1, so 1 over 2, right? A sub 2, now n has a value of 2, okay? So I'm going to put 2 over 2 plus 1, which is 3. So hopefully you see that this, this kind of definition would work for it, and that would be an explicit definition because it jumps and gets you there. Coming up with a recursive definition with this kind of sequence would be really hard. The recursive definitions are pretty easy with arithmetic and geometric ones, and hopefully you see that's because they're so consistent. You're always adding the same thing, you're always multiplying by the same thing. So you'll see that the recursive definitions for those are a lot easier to come up with. Whereas, like, with this one, the explicit one's a little bit hard, but the recursive, yeah, we'll just forget that one. Let's look at a couple other sequences, okay, that you might come across. Let's look at something like this, okay, 1, 4, okay, 9, 16, 25, 36. Okay, so hopefully you've seen those. Those are perfect squares. Let's see if it matches the definition of any of the things we've had before. Okay, what I could do is test if 4 minus 1, that's a common difference of 3. 9 minus 4, that's going to give a difference of 5. So the common differences are not the same, but the common differences are interesting in this case. 1, 4, 9, 16, 25, 36. They do have an interesting pattern for the differences, right? It's like I add 3, I add 5, I add 7, I add 9, right? You get the point. I add 11. So you could kind of come up with a way to generate this one recursively. I'll leave that open-ended for right now, but because there is a pattern to what you're doing, but it doesn't fit an arithmetic sequence because you have to, you know, obviously add the exact same thing. from term to term to term. Okay, neither does it satisfy a geometric one. Let's see what that one would look like. So to test for that, I could do is 4 over 1. So that would be that first ratio. That, of course, is a ratio of 4. And then I would 9/4. Well, you know, 9 over 4 is, of course, not equal to 4. Or neither is the next, you know, difference, or next ratio thing would be 16 over 9. That's obviously not equal to 9/4. So none of those ratios are equal. So, of course, it's not going to be geometric either. So again, that's a great example of a neither sequence, but it's a great example of a sequence that's really easy to come up with a formula for, right? So a sub n would just be n squared, right? So I plug in 1, 1 squared is 1, plug in 2, 2 squared is 4. So again, hopefully you see that a parabola would underlie that particular shape. That's kind of less important, but in any case, you can see that it doesn't fit arithmetic, doesn't fit geometric, but it is, you know, an easy sequence to work with. Okay, so hopefully that gives you a little bit of background on different sequences and especially arithmetic and geometric and how they work, and then also recursive definitions and explicit definitions. Remember, an explicit definition allows you to jump right to any term you want to immediately, whereas like the recursive ones, you have to give a starter term and then you define each thing in terms of the previous thing. Okay, so I'm going to give you some practice working with those, and hopefully you'll have fun with that.